So this presentation is all going to be about free falling. See, Wile E. Coyote falling like he is, hanging on top of the rock. Well, he's free falling. He's floating through air, being affected by gravity. That's pulling him down towards Earth, accelerating him towards the surface. So Galileo kind of had his famous experiment he did around his theory of gravity, which is that objects are going to accelerate at the same rate, no matter what size they are, towards the Earth's surface. So he dropped two balls off the Leaning Tower of Pisa, and you can see both of those two balls hit a person at about the exact same time, even though they're different sizes and shapes. They didn't really hit a person when he did this experiment, but his theory was that the object doesn't matter. It's only the effect of how strong gravity is that's going to matter. Every object is going to fall at the same rate due to the gravitational force. So you might think about this. Normally, you're like, okay, I dropped two things. Maybe one's a feather, one's a bowling ball. They're not going to land at the same time. However, we watch this video on the right, you're going to see that if we suck out all the air, we put this in a huge vacuum tube, and they drop the feather and the ball at the exact same time. Well, now, since we've gotten rid of air resistance, both things land at the exact same point, at the exact same time point. So even though when you drop things, you might think, hey, this is going to land before that one, the reason it's happening isn't because of the mass of the object, it's because of actually the air around the object that's causing it. If we can get rid of that air, things drop at the same rate. So now the question becomes, well, what is gravity? Where does it come from? Well, it comes from the mass of objects. And it's a force that acts between two different objects. So here's the equation for figuring out how much force you're going to get out of two objects interacting with one another. So you might have like object 1 here and object 2 over here. Okay, and object 1 and 2 are going to pull on each other. So 2 is going to pull 1 this way, 1's going to pull 2 that way. And the strength of that force between them is going to be based on the mass of the first object, the mass of the second object. The bigger they are, the stronger the force is going to be. And this gravitational constant, okay? And we're not going to use this equation, also you don't really know what it is. It's just a constant, just something you multiply it by. And then it's going to divide by the square of the distance between the two, meaning that as they get further and further away from each other, the gravitational force is going to decrease, but not even just decrease linearly, but decrease exponentially. So here's our basic equation. So what's happening is that we drop something, and that gravitational force causes the mic to drop. So the Earth has a mass, the microphone has a mass. The Earth pulls the microphone towards it, it drops. Gravity works, right? Well, the other aspect of that, though, is at the same time that the microphone is dropping, it's also pulling up on the Earth. Okay? The difference is the Earth is too big and the microphone can't actually pull the Earth towards it or move it. Their mass is too large. That force is enough to move the microphone, but it's not enough to move the Earth. So when an object is dropped, here's some things we're going to need to understand. The initial velocity of that object is going to be 0. Makes sense. It's not moving when we drop something. Objects are going to accelerate towards the Earth. Okay? Gravity is causing an acceleration. That force is acting on it. The rate of acceleration is going to remain constant for any object. Doesn't matter what the object is. Okay? It's going to remain constant. Therefore, all our motion equations still apply that we went over. The only difference is that the variable a is replaced with the acceleration due to gravity g, and that's going to be 9.81 meters per second squared. So basically, we've taken a variable and turned it into a constant by using gravity. So hopefully that'll make sense. So a couple quick assumptions though for free fall that we're going to make. The only force acting on an object is gravity. So object is in free fall. The only force acting on that object is the force due to gravity. That's because air resistance will not be a factor. Okay. So even though normally air resistance is going to be a factor, we're not going to factor it in because of the difficulty in kind of dealing with the math behind it. And air resistance would change based on what the object is, and it's going to change a lot based on what the object is. We're not going to test everything we use. We'll understand that there's going to be air resistance, but for our basic equations, we're going to assume it's not a factor. Third assumption is that acceleration is constant on Earth, even though, based on the equation we saw, the further we get from distance from the central core of the Earth, the less acceleration there's going to be because the less force there's going to be. We're going to assume that the acceleration is the same everywhere, that 9.81 meters per second squared. So the equations that we dealt with before, what are going to happen to them? Well, we're going to have the exact same ones. Like I said, we're just going to replace A with G. So we have D equals V average times T. V average is VF plus V average 2. Same thing. VF equals VI plus G times T instead of A times T. All these equations are exactly the same. One of the things that happens, though, when VI is 0 is some of these equations are going to change. So when we're dropping something, VI is 0, this term goes away, which is why we get this equation right here. We also, this term right here will go away. D equals VF squared over 2G. If we know the final velocity of the object, we can find out how far it fell. And this equation right here, this VI squared will go away. So if we want to know the final velocity of an object based on how far it fell, all we need to know is D. All we need to know is that distance, and we're going to know the final velocity because G is now a constant. So understanding that all those relationships is really important when dealing with dropping. We're going to deal with problems where we toss balls up in the air and let them come back down too, but we'll kind of explore that later. I just wanted to introduce you to the basic concepts for free fall, and then we'll kind of further dive into it with our problems and things we discuss in class.